Welcome. Today we're diving into the fascinating world of intermolecular forces. These are the invisible attractions that hold molecules together, shaping everything from the water we drink to the air we breathe. Understanding these forces helps explain why substances have different boiling points, why ice floats, and even why some materials dissolve while others don't. In this video, we'll break down the main types of intermolecular forces, see how they work, and explore their real-life impact. Let's start by defining what intermolecular forces are and why they matter in chemistry and everyday life. Intermolecular forces are the attractions or repulsions between molecules, separate from the stronger bonds that hold atoms together within a molecule. While covalent and ionic bonds form molecules, intermolecular forces determine how those molecules interact with each other. These forces are generally much weaker than chemical bonds, but they play a crucial role in determining the physical properties of substances, such as melting and boiling points, solubility, and viscosity. Without intermolecular forces, matter as we know it wouldn't exist in its familiar forms. There are several types of intermolecular forces, each with its own characteristics and effects. The three main categories are London dispersion forces, dipole-dipole interactions, and hydrogen bonding. Each type varies in strength and arises from different molecular features. Understanding these differences is key to predicting how substances will behave under various conditions. In the next scenes, we'll explore each type in detail, starting with the most universal, London dispersion forces. London dispersion forces are the weakest type of intermolecular force, but they are present in all molecules, whether polar or nonpolar. These forces arise due to temporary fluctuations in electron distribution, creating momentary dipoles that attract neighboring molecules. Even noble gases like helium and argon experience London dispersion forces, which is why they can condense into liquids at very low temperatures. The larger the molecule, the stronger these forces become, influencing boiling and melting points. Dipole-dipole interactions occur between molecules that have permanent dipoles, meaning there's an uneven distribution of charge within the molecule. These forces are stronger than London dispersion forces and are especially important in polar molecules. For example, in hydrogen chloride HCl, the positive end of one molecule is attracted to the negative end of another. This attraction affects the physical properties of substances, such as increasing their boiling points compared to nonpolar molecules of similar size. Hydrogen bonding is a particularly strong type of dipole-dipole interaction. It occurs when hydrogen is bonded to highly electronegative atoms like nitrogen, oxygen, or fluorine. The hydrogen atom becomes highly positive and is strongly attracted to lone pairs of electrons on nearby electronegative atoms. This force is responsible for water's high boiling point and its unique properties, such as ice floating on water and the ability of water to dissolve many substances. Let's compare the strengths of these forces. London dispersion forces are the weakest, followed by dipole-dipole interactions, with hydrogen bonds being the strongest among them. This hierarchy explains why substances with hydrogen bonds, like water, have much higher boiling points than those with only dispersion forces. The strength of these forces also influences other properties, such as viscosity and surface tension. Water is a classic example of hydrogen bonding in action. Each water molecule can form up to 4 hydrogen bonds with its neighbors, creating a highly connected network. This network gives water its high boiling point, high surface tension, and the ability to dissolve many substances. It's also why ice is less dense than liquid water, allowing it to float and insulate aquatic life during cold months. When water freezes, its molecules arrange themselves in a hexagonal structure due to hydrogen bonding. This arrangement creates open spaces, making ice less dense than liquid water. As a result, ice floats, forming an insulating layer on lakes and ponds. This unique property is crucial for aquatic ecosystems, protecting life beneath the surface during winter. Intermolecular forces aren't just a topic for textbooks, they're all around us. They determine why oil and water don't mix, why perfume spreads through a room, and why certain materials feel sticky or slippery. From the food we eat to the clothes we wear, intermolecular forces shape our daily experiences in countless ways. Oil and water don't mix because of differences in intermolecular forces. Water molecules are highly attracted to each other through hydrogen bonding, while oil molecules rely on weaker London dispersion forces. Since water prefers to stick with itself, oil is pushed aside, leading to the familiar separation we see in salad dressings and puddles. When you spray perfume, its molecules spread throughout the air. This happens because of weak intermolecular forces between perfume molecules and air, allowing them to move freely. The process, called diffusion, is a direct result of the balance between molecular motion and intermolecular attractions. Viscosity, or a liquid's resistance to flow, is influenced by intermolecular forces. Liquids with strong forces like glycerol flow slowly because their molecules stick together tightly. In contrast, liquids with weak forces like hexane flow easily. This explains why honey pours slowly while water pours quickly. Surface tension is another property shaped by intermolecular forces. Water's high surface tension comes from its strong hydrogen bonds, allowing small insects to walk on its surface and droplets to form beads. Liquids with weaker forces like alcohol have much lower surface tension and spread out more easily. Boiling and melting points of substances are directly linked to the strength of their intermolecular forces. Substances with strong forces like water require more energy to separate their molecules, resulting in higher boiling and melting points. Substances with weak forces like methane boil and melt at much lower temperatures. Solubility, or a substance's ability to dissolve, is also governed by intermolecular forces. Polar substances dissolve well in polar solvents due to similar forces, while nonpolar substances dissolve in nonpolar solvents. This is why salt dissolves in water but not in oil, and why oil dissolves in gasoline. Evaporation occurs when molecules at the surface of a liquid gain enough energy to escape into the air. Liquids with weak intermolecular forces like acetone evaporate quickly, while those with strong forces like water evaporate more slowly. This explains why rubbing alcohol feels cool on your skin. It evaporates rapidly, taking heat with it. Capillary action is the ability of a liquid to flow in narrow spaces without external forces. It's driven by the combination of cohesive forces between like molecules and adhesive forces between unlike molecules. Water's strong hydrogen bonds make it excellent at climbing up thin tubes, which is essential for plants drawing water from soil. Adhesion is the attraction between different substances, while cohesion is the attraction between like molecules. Both are types of intermolecular forces. In water, cohesion leads to surface tension, while adhesion allows water to stick to glass or plant tissues. These forces work together in many natural processes. It's important to distinguish between intermolecular and intramolecular forces. Intramolecular forces are the strong bonds within a molecule, like covalent or ionic bonds. Intermolecular forces, on the other hand, are the weaker attractions between separate molecules. Both are essential, but they play very different roles in chemistry. Van der Waals forces is a term that collectively refers to all types of intermolecular forces, including London dispersion and dipole-dipole interactions. These forces are named after Dutch scientist Johannes van der Waals, who first described their importance in the behavior of gases and liquids. The size of a molecule affects the strength of its intermolecular forces. Larger molecules have more electrons, leading to stronger London dispersion forces. This is why larger hydrocarbons have higher boiling points than smaller ones, even if both are nonpolar. Polarity plays a major role in determining which intermolecular forces are present. Polar molecules experience dipole-dipole interactions, while nonpolar molecules rely on London dispersion forces. The presence of hydrogen bonding further increases the strength of attraction between molecules. In solids, intermolecular forces hold molecules in fixed positions, giving the material its shape and rigidity. The strength of these forces determines whether a solid is hard and brittle like salt or soft and flexible like wax. Molecular solids such as sugar are held together by these forces rather than by strong chemical bonds. In liquids, intermolecular forces are strong enough to keep molecules close together but not in fixed positions. This allows liquids to flow and take the shape of their container. The balance between these forces and molecular motion explains why liquids have definite volume but no definite shape. In gases, intermolecular forces are very weak, allowing molecules to move freely and spread out. This is why gases have neither a definite shape nor a definite volume. The weak attractions between gas molecules explain why they can be compressed and expand to fill any container. Phase changes, such as melting, boiling, and freezing, involve breaking or forming intermolecular forces. When a substance melts or boils, energy is used to overcome these forces. The stronger the forces, the more energy is required, which is why water has a high heat of vaporization. When substances dissolve, intermolecular forces between solute and solvent molecules must be compatible. If the forces are similar, dissolution occurs easily. This is why salt dissolves in water but not in oil, and why sugar dissolves in tea. Intermolecular forces are essential in biology. They help proteins fold, DNA strands stick together, and cell membranes maintain their structure. Hydrogen bonds and other forces ensure that biological molecules function properly, supporting life at every level. Polymers like plastics and rubber rely on intermolecular forces for their flexibility and strength. The arrangement and strength of these forces determine whether a polymer is stretchy, rigid, or somewhere in between. This is why different plastics have different properties. From the softness of cotton to the hardness of glass, intermolecular forces shape the materials we use every day. The way molecules interact determines whether something is soft, hard, flexible, or brittle. Understanding these forces helps scientists design new materials with specific properties. Temperature affects intermolecular forces by increasing molecular motion. As temperature rises, molecules move faster, making it easier to overcome these forces. This is why solids melt and liquids boil when heated. Cooling has the opposite effect, strengthening the attractions between molecules. Pressure can also influence intermolecular forces, especially in gases. Increasing pressure pushes molecules closer together, making intermolecular attractions more significant. This can cause gases to condense into liquids, as seen in pressurized gas cylinders. Phase diagrams show how temperature and pressure affect the state of a substance. The boundaries between solid, liquid, and gas phases are determined by the strength of intermolecular forces. Stronger forces shift these boundaries, requiring more energy to change phases. In mixtures, different substances interact through their own intermolecular forces. The compatibility of these forces determines whether substances mix evenly or separate. This is why some liquids form layers while others blend together seamlessly. Detergents work by disrupting intermolecular forces. Their molecules have both polar and nonpolar ends, allowing them to interact with water and oils. This breaks up grease and dirt, allowing them to be washed away. It's a practical example of how understanding intermolecular forces leads to useful products. In medicine, intermolecular forces affect how drugs interact with the body. The ability of a drug to dissolve, reach its target, and bind to specific molecules depends on these forces. Designing effective medicines requires a deep understanding of molecular interactions. The texture of food, whether it's creamy, crunchy, or chewy, is influenced by intermolecular forces. These forces determine how molecules in food interact, affecting everything from the smoothness of chocolate to the stretchiness of cheese. Food scientists manipulate these forces to create new textures and flavors. Cosmetic products rely on intermolecular forces for their texture, stability, and effectiveness. Creams, lotions, and gels are carefully formulated so that their molecules interact in just the right way, ensuring smooth application and long-lasting effects. Cleaning products use intermolecular forces to break up dirt and stains. Surfactants, for example, lower the surface tension of water, allowing it to spread and penetrate grime. This makes cleaning more effective and efficient. Adhesives like glue and tape rely on intermolecular forces to stick to surfaces. The strength and type of these forces determine how well an adhesive works and what materials it can bond. This is why some glues work on wood but not on plastic. Weather phenomena like cloud formation and raindrop creation are influenced by intermolecular forces. Water vapor condenses into droplets when molecules attract each other strongly enough. These tiny interactions have a big impact on our climate and daily weather. Nanotechnology harnesses intermolecular forces to build tiny devices and materials. At the nanoscale, these forces become especially important, allowing scientists to create new materials with unique properties for medicine, electronics, and more. Environmental science relies on understanding intermolecular forces to address pollution, water treatment, and climate change. These forces affect how pollutants spread, how water is purified, and how greenhouse gases interact in the atmosphere. Summary: intermolecular forces are the hidden connections that shape our world. From the properties of water to the design of new materials, these forces influence countless aspects of science and daily life. By understanding them, we gain insight into the behavior of matter and unlock new possibilities for innovation and discovery. Thanks for joining us on this journey through the world of intermolecular forces.